Okay. So, hope everybody's having a good day. It's Tuesday. A couple of items. Don't forget, Thursday morning is what deadline? Okay, the exam. Okay, I've already had several people come in. Uh, Still got a couple of days. Please take advantage of that. 2 weeks from Friday is the end of the 6 weeks already. Friday morning by 8:05, that's the deadline for what? The Happy Minutes, but only from the week of the 14th to the 18th when I recorded them as homework and quiz grades. So if you fall under one of those two categories, please take advantage of that. Get that taken care of. Okay, I'll be here at 7:45 in the morning. Speaking of Thursday, what's happening that day? You have a quiz over double angle identities. Okay, so please make sure you have those down by the time you walk in on Thursday. Again, I hate to use the word memorize, but we need to know those. All right, should not be too bad if you know the identities. Okay, as of right now, the test is scheduled for next Thursday. If I do need to move it for whatever reason, I'll let you know, but let's just go ahead and plan on right now it's next Thursday. So we have a little over a week before that happens. And I believe that's all I have, unless anybody has any questions. Okay. Now, today's lesson is going to be pretty short. I only wanted to take one period to go ahead and do it. It's more an introduction than anything. There are going to be parts of this lesson that you're not going to understand, and that's perfectly fine. Some of it's just going to be a preview of what you're going to be seeing next year in calculus. How many people know for certain they are going to calculus? Okay, so this lesson is going to be really important to you. If you're not going to calculus, probably not so much. I'm not going to quiz or test you on it. I'm not going to give you any homework on it. But if you are going to calculus, yes. Okay, so the double angle identities, we've talked thoroughly about those. Now, these are what we call the half angle identities. They're not as useful to us, and I'm not going to be doing anything with them, but you could potentially see those next year. So I just went ahead and gave those to you more just to kind of make you aware of those. What I want to work with are going to be the power reducing formulas. Okay, so if you have different powers on a trig function, a lot of times there are certain instances where we need to work with a reduced power. We don't want something like sine to the sixth. We want something that's going to be easier to work with. And once we go through a couple of examples, then I'll kind of give you the big picture, but that's also where some people are probably not going to understand what I'm referring to, and that's perfectly fine. Okay, right now we're just dealing with the formulas and basically the algebra. So here they are. Sine squared of u equals 1 minus cosine of 2u divided by 2. Cosine squared of u equals 1 plus cosine of 2u over 2. And third, we have tangent squared of u equals 1 minus cosine of 2u over 1 plus cosine of 2u. Now, think back, just kind of forget about that third formula right there. Tangent squared, well, what would that be just using the quotient identity? How could I rewrite tangent squared? Sine squared over cosine squared. Now, that is the Pythagorean, but yeah, the quotient identity is just sine squared over cosine squared. So if you take these previous formulas, this fraction divided by this fraction, if you were to simplify, that's exactly where you'd get the formula that we have for this guy right here. Ultimately, those twos are going to cancel. But one other thing I want you to notice, and I brought this up before, whenever you apply this formula, certain patterns are going to hold true. You'll notice I have a coefficient on u of 1. What happens in the formula? It becomes a 2. So when you apply the formula, it doubles that coefficient. It's going to be real important to us. Okay, well, why don't we go ahead and get right to it. Let's do an example. Now, I'm going to kind of skip around here. Let's do this one, the third example first. Sine cubed of theta. Let's look at this one. So I want to apply the power reducing formula to sine cubed of theta. Now, some of our answers today will not be final. You would actually want to continue these further, and I'm going to show you how you could do that. But, okay, we're going to get there. Now, think back to your exponent rules. I can only apply the power reducing formula if I have sine squared, right? So is there something I could do here? Yeah, that's right. We can just break it apart. Sine cubed of theta would be the same as saying sine of theta times sine squared of theta. Remember, treat the trig function as just a variable. X times x squared would be x cubed. Same thing here. Now, while I'm going to have this sine function just kind of hanging out there for a second, I can apply the power reducing formula to sine squared. So what was that version? What was the formula? Okay, so 1 minus cosine of 2 theta. Remember, it still doubled the coefficient on my variable, and we're going to divide that by 2. Okay. Well, now, I'm going to go ahead and redistribute that sine across the top. Kind of pretend that it's sine over 1, and we just multiply. So this would be sine of theta minus, now that would be sine times cosine 2 theta. So sine of theta cosine 2 theta, and that's still all over 2. Now, that by no means would be our final step, but we are going to go ahead and stop there. Because one of the things you're looking for when you're using the power reducing formula, you don't want to have any products of different trig functions or even the same trig functions. Okay? There are additional identities that exist that we are not going to be able to cover in here. Really, we just don't have the time, and it's not necessary for what we're doing. So the reason this guy wouldn't be done is basically because of this product. Whoa. Yeah, that just broke down. Okay. So give me 1 second. I will pull that right back up. Too much math. Retrieve some of your life. Would you like to retrieve? Sure. Waiting. Waiting. Oh, and good, it didn't even have my work. Okay, so let me see if I can catch up. This one was the easy one. I'm glad it didn't do that on the bigger one. Let's see, what do we have here? We got down to what we said a final answer was sine of theta minus sine of theta cosine of 2 theta divided by 2, right? Okay, so that's what we said our final answer was going to be. But you wouldn't want to stop there because you have a product of trig functions, and you want to simplify that even further. There are identities that we call the product to sum formulas. And they're actually very specific about the order that you would have to use those in. So for example, that product was sine times cosine, right? So I would want to use the first one in order to continue simplifying that problem. Okay, so again, this is where we start getting beyond what we're going to do in the class. I'm just kind of throwing this out there. This is stuff that you're going to see. Okay. The important thing today is really just knowing the power reducing formulas and being able to apply them. Okay. All right. Now don't worry about this integration down below. We'll get to that in just a second. All right. Now let's go back to the original problem. Let's go ahead and do sine to the 4th of x. Okay. So I want to apply the power reducing formula and simplify as much as I can. Okay. Well, I need a squared, so any ideas? Yeah, couldn't we say sine to the 4th is just sine squared times sine squared? Okay. So sine to the 4th of x, well, that would just be sine squared of x times sine squared of x. Okay. Now, see, unlike the previous one, I'm going to be able to apply the formula to both of these. What was sine squared of x again? I keep forgetting. It was 1 plus or 1 minus? 1 minus. Okay, so for the first sine squared, I can say 1 minus the cosine of 2x divided by 2. And then for the second sine squared, I'm going to have the same formula. 1 minus cosine 2x all divided by 2. Okay. Now, would everybody agree that one of these expressions, it doesn't matter which one. Okay, dividing by 2, would this be equivalent if I were to say 1/2 times 1 minus cosine of 2x? Because multiplying by 1/2 is the same as dividing by 2, right? Okay, got a text message. So that is equivalent, but I want to go ahead and do that for both of these. I want to pull the 1/2 away from the first, and I want to pull the 1/2 away from the second. So what will I have out in front? 1/4. Okay, so that's my next step. So this is going to be 1/4 times 1 minus cosine of 2x times 1 minus cosine of 2x. Or you could write it as 1 minus cosine 2x squared. Does not matter. Okay. Now what do you think my next step would be? How would I continue the problem? Yeah, FOIL. Okay, let's go ahead and multiply, right? So take, let's say 45 seconds. Multiply these together by FOIL. Okay. You're looking for a trinomial. Let's see if we can all get the same thing. And even that won't be our last statement because we're going to be able to do something with what we get. So we are going to have the 1/4 out in front. Okay. Yes. Oh, did someone not? Hey, there's one. Okay. Thank you. Okay. So right now we are foiling 1 minus cosine 2x with itself. Okay. Excuse me. Okay, can anybody tell me what trinomial I should be ending up with? Okay, so 1 what? Minus 2 cosine 2x. There we go. Plus cosine squared 2x. Remember, it's the cosine that's squared, not the input, not the 2x. Okay, does anybody want me to multiply that out to show how we got those? Any takers? Would you like me to multiply that out to see how we got that?
Nah.
Sure.
Okay. Nah, I got that. Just flip.
Okay. Yeah, as long as the terms are there, the order doesn't matter.
Nice.
Yeah, you're fine. Okay, now there is something we can do with this. Does anybody notice it now? We have cosine squared, and we are dealing with power reducing formulas, so I can apply that to cosine squared. Okay, so write out what you think this is going to become. Remember that pattern I talked about? 1/4 times 1 minus 2 cosine of 2x. Let me give you a few seconds. Okay. So Christian got it. Okay. So I know Christian already got the right answer. What's going to happen when I try to apply the formula to cosine squared of 2x? What's it going to become? Okay, it's going to be 1 plus cosine of 4x. Remember, it doubles that coefficient over the 2. Okay. All right, and then we're going to go ahead and do just a couple more things, and then we're going to go ahead and call it quits on this problem. Like we did before when we first started, where I pulled out the 1/2 from each of those and I got the 1/4, I want to do the same thing to this 1/2. I don't want to have any fractions. So I'm going to pull the 1/2 out, but that's going to have the same effect as dividing those other terms by 1/2 as well. Okay, so first, that 1/4 would become what? 1/8, because I pull out an additional 1/2, right? So that would be 1/8 times, what would the 1 become? Not 1. It wouldn't be 1/2. It would be 2. Okay. Because think about it, if I were to rewrite this, let me go ahead and give myself a little more room. If I kept it as a product, 1/4 times 1/2, if I were to redistribute the 1/2, I'd want to get the original ones that I had. Okay. So then this would be minus what? Minus 4 cosine of 2x. Because see, half of 4 would give me the 2. All right, and then the numerators would be right there. So plus 1 plus the cosine of 4x. Okay. All right. And then there is only one last step. In fact, does anybody notice what we can do? We could combine like terms. In fact, we only have a couple of constants. So I would go ahead and say 1/8 times 3, the 2 plus the 1, minus the 4 cosine of 2x plus the cosine of 4x. Could I go ahead and combine those cosines? Why not? They're both cosines. One's a 2x and one's a 4x, so they're not like terms. So that is going to be as far as we could go. Remember, today was just showing you the formulas, getting a little bit of work with them. Okay? You'll really start to use them when it comes to calculus. Now, speaking of calculus, is there anybody out there wondering what you would do with them? Okay, this right here. Like I said, there are specific times where these power reducing formulas are going to be very useful to us, and this is one of those times. This is integration. Okay, basically it's what's called the antiderivative. Now hopefully that sounds a little familiar because I taught you in the first semester how to find the derivative. Does anybody remember that? Do you remember the difference quotient? We had f of x plus h minus f of x all over h. And we took the limit as h approached what? 0.
Right.
Okay. Does that look familiar? Very few people have remembered that today. Zach, you do remember that? Really? We did do it at the beginning. Okay. All right, but here's the thing. We did enough problems where people started to figure out what the patterns were. I didn't teach you the shortcuts. I'm going to leave that to Mr. Heinrich, but you did start to pick up on what they were. Can anybody tell me if I were to give you something like, 2x cubed, what's the derivative? Does anybody remember the patterns? 6x squared, very good. Okay, the derivative is 6x squared. Now, this little symbol right here, what looks like a really elongated S, that's what we call an integral. This means to take the antiderivative. Okay, so we just took the derivative of 2x cubed and got 6x squared. Well, when I want to find the antiderivative, that means I want to work backwards. What would I take the derivative of to get the expression that I have? So while 6x squared is the derivative of 2x cubed, I can say that 2x cubed is the antiderivative of 6x squared. And that's what you're doing here. But the problem is you can't integrate cosine squared. Okay, when you start dealing with those even powers, you can't integrate it. You can't find the antiderivative. So what we do is we rewrite it using the power reducing formulas of something that we can take the antiderivative of. In fact, do you notice, does this second step look familiar?
Yes.
Remember, what was cosine squared of x? What was the power reducing formula for it? It was 1 plus cosine 2x, right? Well, all I did was pull the 1/2 out in front. Now see, this is something that I can differentiate. I can go ahead and take the antiderivative of that, and that's actually what you end up with. So this is probably the point where I'm losing some folks, and that's okay. I'm just kind of giving you a big picture. If you're going into calculus, you're going to see a lot of this next year. Okay, you're going to be very, very, very acquainted with that. Okay, it's actually not too bad. Everything is kind of scary when you see it for the first time, right? Okay, so you'll be okay. But we are not doing that in here. Will I ever give you an antiderivative? No, I will not. No test, no quiz, no homework. This is just an introduction, like I said. Okay. Now, for those of you going into calculus, I would encourage you, take this sine to the 5th, apply the power reducing formulas, see if you can come up with a simplified version. Okay. Now, if you're not going into calculus, if you know that for sure, probably not a big deal, okay, but I would really encourage you, if you're going into calculus, you're going to need that practice. Okay, so tomorrow when you come in, I'll have this up on the board, and Hopefully we'll get to the same response. Okay. So good, good, good. So we're going to go ahead and put the power reducing identities to the side. I showed you those. This is what we want to spend our time on now. This is a preview of what's coming up starting tomorrow. We want to solve equations, specifically trig equations. Okay. Now, solving a trig equation is really no different than solving a normal equation. You're wanting to find all the angle measures that are going to make your statement true. So here's the first one. Cosine of 2x equals 1/2. What are all the angles x that make this a true statement? Okay. So there are a couple things. If you just have, and you're going to see these as we go along, but if you only have an equation with one trig function, you'll probably want to try to isolate the trig function as we did here. If you have multiple trig functions, you'll probably want to use one of your identities. You'll be using factoring, algebraic techniques, a lot of the different styles you used on normal equations, okay, to go ahead and solve these guys. So let's just get right to it. Cosine of 2x equals 1/2. Now, because 1/2 is positive, what two quadrants would that place cosine in? Okay, 1 and 4. That's where cosine's going to be positive, right? So I've got a grid here. I'm going to go ahead and draw a triangle in quadrant 1, but also a triangle in quadrant 4. And that's the thing when you're solving these equations. We're going to use triangles just like we use triangles for the unit circle. We use triangles for the inverses. We've used triangles a lot in here. Okay, so you could potentially be solving an equation where every one of your quadrants is going to have the same triangle. Isn't that right, Ford? Absolutely right. Okay. Now, 1/2. So what is cosine's ratio? It's x over r, right? Okay, so the adjacent over the hypotenuse. So you'll notice these two triangles share one side. It's that x. So they both have that length 1, and each radius is going to be length 2. And what you're going to notice as you go through these, it's always going to be the same triangle. It's just going to be oriented in a different quadrant. Okay. What would the height be if I were to use Pythagorean theorem? It is square root of 3. But what's the difference about this one? It's negative because of the quadrant it's in. And, that's one thing you'll want to be really careful about. Okay. Now, does anybody want me to run through Pythagorean theorem and show you how we got that? Hey.
I don't want you to run through, but how again did you determine what quadrants the triangles would be?
Okay, good question. How did we figure out these triangles would be in quadrants 1 and 4? Okay, so Christian says all students take calculus. What does that mean?
A is 1.
Yeah. So all students take, and I'll just put calc. Okay. So remember, it's the first letter of each word. So A actually does stand for all. All 6 trig functions will always be positive in the first quadrant. But what 2 are going to be positive in the second? Sine and cosecant. The S stands for sine, and we have its reciprocal. What about the T? Tangent and its reciprocal cotangent. And then C stands for the cosine and its reciprocal secant. So had this been cosine of 2x equals negative 1/2, then my triangles would have been in what? Where would cosine be negative? Oh, 2 and 3. Because think about it, what variable does cosine represent? Does it represent the x or the y?
The y. X is the x-axis. X is the x.
Yes. So cosine is the x. So think about, what quadrants would x be negative? Well, it'd have to be negative in 2 or 4, or excuse me, 2 or 3, because you have to move left of the origin. Here, x is positive in 1 and 4, because you have to move right of the origin. And you do the same thing for y. And even when we get to those equations that start dealing with tangent and secant, you're just going to be thinking of those in the same way. Where would they be positive and or negative? Okay. All right, so is everybody okay with how I got the triangles? Okay. Now the goal is we're trying to solve for x. I want all the values. Now, typically, it's going to be broken up into one of two ideas. Either you're going to be given an interval, as this problem is right here. It's going to say, what are all the solutions in one rotation between 0 and 2 pi? Or I could say, what are all the solutions to this equation? What are all the real? And not give you an interval. That would be every possible solution you could come across. I would recommend you writing out the general form and then using that to find your specific if necessary, especially on problems like these. Okay, so let's just go ahead and get started. What kind of triangles are these? Okay, these are 30, 60, 90. Is everybody okay with how we know that? Who said no? I could have sworn I heard a no. Okay, so you said yes. Okay, so Satish is okay. Now here's what's really important. What's this angle right here? Is that 30 or is that 60? That's 60. We always are going to start rotating from standard position. That means the positive x-axis. Okay. So one of my answers is going to be 60. Okay. But that means this one would be 60 as well, because remember, it's the same triangle, right? But how far would I have to rotate to have a reference angle of 60 left? 300. Okay. All right, so I'm going to go ahead and say 300 degrees as well. Now, the thing about these equations, if you need to go ahead and work with degrees, that's okay, but our final answers are always going to be in radians. So what is 60 degrees as a radian? Okay, that's pi over 3. So this would be pi over 3. Okay, and this one would be, what is 300 degrees? Five thirds pi. 5 pi over 3. Now you could look at your unit circle, or you could just multiply by what? Pi over 180. You could convert that. Okay, but the more of these equations you do, you're going to become very, very familiar with the unit circle, those 16 points that we have. Now here's the thing. If I wanted to go ahead and say what are every possible solution, for these answers that I got, I'd go ahead and plug on 2 pi n, where I'm going to say n is an integer. You okay? Okay. I'm going to go ahead and say plus 2 pi n. What am I referring to when I do this? What do we call angles that come back around and stop in the exact same position? Different measures, but the same position. Coterminal. These general forms would find me every single angle that's possible, no matter how many times I rotate. Does everybody remember what an integer is? What numbers make up the integer group? So it's negatives, they're positives, and 0. So whole numbers are opposites and 0. No fractions, no decimals. Okay. Now, if this were a normal problem, if it said cosine of x equals 1/2, we'd be good to go. But what did I just say when I read that problem? I said cosine of x equals 1/2. What is this equation? This is cosine of 2x. So these aren't quite my answers just yet. I need to solve for x. I don't want 2x. So if it's a simple fix, all I got to do is divide through by 2. Now, you won't always have to do this. If it's already just a single variable, you're good to go. If it's not, it's either going to be one of two things. It'll either be 2x or 1/2. So you'll just have to change it appropriately. Okay. So what would this first one be? What is pi over 3 divided by 2? Pi over 6 plus what? Pi n, because when I divide by 2, the 2's cancel, right? And x is going to equal 5 pi over 3 divided by 2. 5 pi over 6 plus pi n. Now, let's go back for just a second. Why did I add 2 pi n to each of these? Was that specific to the problem? Think back when we first graphed these functions. I'm thinking for a word that starts with a P. What, Aiden? Okay, what are you talking about when you say period? What was the period of a function? What did that mean? That's the number of radians needed before the graph does what? before it repeats, right? Okay. Well, what is the period for cosine? It is 2 pi. Okay. Because also here, 2 pi represents 1 revolution around to get back to that same position. Is everybody okay with that? Now, there are only 2 trig functions where you will not be adding 2 pi in. You'll add something different. What am I possibly referring to? What's wrong with tangent and cotangent? Their periods were only pi, so you'll be adding pi into both of those. So on this problem right here, if I were to say I want all the solutions that are possible, basically every coterminal angle, this is what you're going to give me. It'll be that general form. Or the problems could be more specific. I could give you some kind of interval. Like in this case, between 0 and 2 pi. 1 revolution, 1 counterclockwise revolution. If you're needing to do that, that's why I like to have the general form ready to go. You can take values of n and just plug them in. Like let's start with 0, 1, and 2. Okay. We want to go far enough that if I get an answer that is outside of that interval, I know I can stop. But I want to get every answer in the interval. Why don't I need to go negative? I mean, I could. It would. Because what's my interval? Between 0 and 2 pi. If I were to start taking negative values of n, that would rotate me clockwise. Okay. So we want 1 counterclockwise rotation. So let's plug in. While this is the general form, these will give me every single answer I could ever possibly want. I only want the answers in that interval. So let's start with 0. So what is pi over 6 plus pi times 0? Yeah, that's just pi over 6, right? Now I'm going to plug that same value into the other one. You'll notice I'm going to do it for both. That's going to keep my answers in order. So what is 5 pi over 6 plus pi times 0? 5 pi over 6. Whoa, whoa. This thing is tripping today. 5 pi over 6. Okay. So n equals 0 is done. There you go. My speak is on fleek. Okay. I think the screen got triggered. Maybe it's salty. I don't know. That's correct, right? Salty. See, that's correct. You know, there you go. Okay, now let's try this one. N equals 1. So I want pi over 6 plus pi. So Christian's absolutely right. It would be 7 pi over 6. Does 7 pi over 6 belong to that interval? Is it less than 2 pi? Yes. So 7 pi over 6 is an answer. Now I'm going to plug the 1 into the other one. 5 pi over 6 plus pi. Well, wouldn't that just be 6 pi over 6? And that would give me what? 11 pi over 6. Would that belong to the interval? 11 pi over 6 is less than 2 pi. Okay. So that is another solution. So that takes care of the 1. See, now I'm going to the 2. So depending on your interval, it might take just a little bit to find those solutions, or you might be able to find them pretty quickly. Let's plug in 2. So now I need pi over 6 plus 2 pi. So what is 2 pi with a... Yes. So what is 2 pi over 6? 2 pi with a denominator of 6. So that's pi over 6 plus 12 pi over 6, right? Which will give me what? 13 pi over 6. Does that belong to the interval? No, 13 pi over 6 is larger than 2 pi, so that is not one of the solutions I'm looking for. So if that one is too large, I'm willing to bet that the next one is going to be way too large as well. So there's no sense in my continuing. There are 4 exact locations where cosine of double the angle would give me 1/2. Okay. So that's how the equations are going to break down. I'm either going to ask for the general case, meaning I want every angle possible, every coterminal angle, or it's going to be specific to an interval. And it could vary. You know, a lot of times you're going to see it between 0 and 2 pi. It could go between negative pi and pi. It could go between 0 and 4 pi. Just depends. Okay. But in the beginning, every one of these equations will be based on what type of triangle? These special right triangles, 30, 60, 90 or 45, 45, 90. Once I feel we're comfortable with those, then we'll move on to some that are not based on those triangles. Okay. How we doing? Does anybody have any questions?
This isn't going to be on the test, right?
Actually, if the test that I'm creating right now, the majority of the test is solving equations.
Nice.
Yes. But the power reducing is not on there.
Okay.
Now, see, we still have over a week to still practice.
Oh,
Okay, so
there's going to be homework?
oh, there will be homework, yes.
Okay.
Yeah, you'll get a chance to practice. Okay. All right, so let's try this. Sine of 2x equals 0. Okay. Now, where would I draw my triangle or triangles? What quadrant? Oh, now be careful. Why is this one different? It's kind of a trick question. It's a quadrantal. 0 is neither positive nor negative. So this one I really can't draw my triangles. But again, just think about the unit circle. What locations would your y value be 0? Look at those ordered pairs. What quadrantals would that apply to? Positive x or y, negative x or y. Positive what? Positive y? Well, on the positive y-axis, we have the ordered pair 0, 1. That wouldn't be because we're looking for where the y values are 0. Now, if it were cosine of 2x equals 0, that would be a location.
It's going to be on the
It's got to be on the x-axis. So we have this one right here at 1, 0. See, there's a y value of 0. Okay. So this occurs at 0 radians. Okay. And this other one here is at negative 1, 0. It occurs at pi radians. So see, I found the locations where sine is going to be 0, right? So I'm going to set 2x equal to each of these. 2x is equal to 0. 2x is equal to pi. But I'm not interested in the interval yet. I want every solution possible. So what do I need to add to these? 2 pi n, where we're going to say n's an integer. N determines the number of times in what direction we're going to rotate. So plus 2 pi n plus 2 pi n. Now remember, if it was just x, that problem would be done. Okay? We wouldn't have to worry about anything. But it's 2x, so we have to divide through. What would the first one be? Yeah. So 0 plus pi n, so I'm just going to go ahead and say pi n. Okay. What would happen if I divided the second one by 2? Ooh. Well, we'd have pi divided by 2, so that would give me pi over 2 plus pi n, because the 2's cancel. There you go. So if I wanted an expression that gave me every single infinite angle that would make that true, I'd be done. Okay. But now let's go ahead. Let's actually find the specific answers that are on one interval between 0 and 2 pi. How did we do that before? Okay, yeah, we took values of n, which determined our rotations, right? So n equals 0, n equals 1, n equals 2. Now, depending on your interval, depending on your expression, it's not always going to end at 2. It's just that these are basically going to do that, okay? So let's plug in 0. What's 0 times pi? 0. So that is my first answer. That's the first value that makes this equation true. Now, pi over 2 plus pi times 0. That would be pi over 2. Okay, so that takes care of the 0. I plugged it into both general cases. Okay, now let's try 1. So pi times 1, pi. And you'll notice if you do it in this way, not only are you getting the answers, but they are in order. You got a great little solution set going. Okay. And now, what about this one? Pi over 2 plus pi times 1, so plus pi. Christian says 3 pi over 2. He's absolutely right. Okay. And also, will it always be 4 answers? Not always. Again, it depends on your trig function, depends on what you're solving for. Okay, you could have multiple answers like this. You could have 1 or 2 answers. Okay. Excuse me. Let's try the 2. So pi times 2. 2 pi. Now, would I want to include that? Why not? Because it is strictly less than. Okay, so 2 pi would not be included here. So if 2 pi doesn't work, would 2 work for the other one? No. So I can go ahead and stop there. And in fact, is everybody okay why we don't include the 2 pi? Because 0 and 2 pi, what kind of angles are those? They're coterminal. So I've already got that angle at 0. Does that make sense? Okay. All right, so this is where we're headed. This is where we're going to be spending a lot of our time, at least over the next week and a half. Any questions? Okay. So don't worry, we're going to have a lot of practice. You're going to have homework. Okay. We're going to have, some quizzes, all that good stuff. Okay. All right. Solving equations, a lot of fun. All right. So let me go ahead and shut this down. Whoop, no. Ugh.